All right, we also have vertical and horizontal shrinking and stretching. So again, if your number that you're looking at for these is on the outside, then I like to say it affects the outputs. So if you have some number on the outside of your function, it's going to take that original function and either stretch it or compress it or shrink it. Now your x values stay the same. This isn't like a dilation. Like if you were to be changing a graphic on your phone or something like that, this is literally just the x value stays the same and the y values either get a little bit bigger or a little bit smaller based on what that a value is. If a is greater than 1, then the graph is going to be stretched. If a is between 0 and 1, then the graph is going to be compressed or the y's are going to shrink. And if a is negative, then there's going to be some type of stretch and compression. We'll talk about that in another video. So in this question here, this is the population of fruit flies, and let's say the scientist is comparing a population Q, and they follow the same growth patterns, but it is twice as large, and sketch a graph of that. So one thing that we could do is we could write Q of t is twice as big as P of t. So each and every y value that I know for sure should be twice as big. Then you can just follow that same general pattern to sketch your graph. If you have a, let's say something, just so we have another example here, maybe it was only half as big. So let's maybe say like R of t was half, so like a third population. Then you would only go half as high for those ones. You might also have a horizontal compression. So again, if your number is inside with your inputs, with your x's, that affects your x-axis. Now, because you're inside, just like when we had horizontal shifts, and if this was like f of x plus 1, then you actually moved left 1. And if this was f of x minus 1, then you actually moved right 1 because it's the value of h that determines that. And there's that negative on the inside. And you kind of have this like opposite kind of feel to it. Similar things are going to happen with your horizontal stretch or compression. So on the inside of your function, if b is greater than 0, then you're actually going to have a compression by 1 over b. So notice like here on my graph, I have y equals x squared. Well, if 2 is on the inside, then each x value then gets cut in half that I know here on my graph. And like 9 goes to 1.5. And then if you have a number between 0 and 1, in this case, here, like 1/2 or 0.5, then that's going to then make your function on the x's go twice as big, or like the opposite of what you think would happen. And again, if your b is negative, then we're going to have a reflection, and we'll talk about that in another video. So suppose a scientist is looking at that same fruit fly, and there's a new population R. We'll just call this R again. That's totally fine. But the processes go through the lifespan twice as fast as the original population. So their lifespan then must only go to here, right? Because they are going to be aging or going through these fruit flies twice as fast. So 1 hour is the same as 2 hours. So we're going to start here still, but then we need to make that completion happen twice as quickly. So again, any of my known points, I'm just going to pull in here, and then I'm going to have like a very similar graph to that there. All right, let's go ahead and write this. So then r of t in this case, right, it needs to go twice as fast. So 2 would go on the inside of my function because it affects my inputs, it affects my x's, or in this case, my t values.